There we go. Okay. We are on page 25. 25.
Okay, let's keep learning about ionic bonding. The first thing I want to talk about is why electrons move from sodium to chlorine and not from chlorine to sodium. Okay, so in the first step of ionic bonding, this one electron from sodium moves over here to chlorine to fill this one space. But people often ask, why couldn't these 7 electrons from chlorine move over and fill these 7 empty spots in sodium? Well, that's a great question. The answer has to do with a topic called electronegativity. Okay? Electronegativity is a measure of how badly an atom wants electrons. The higher an atom's electronegativity, the more greedy it is for electrons.
So if any of you are interested in learning a little bit more about electronegativity, I can throw something together for you. But at this point, it's a grade 11 topic, so you really don't need to know it, which is why it has a black diamond beside it. So if you do want to know what it is, it's a measure of how badly an atom
The more it
wants electrons. So electronegativity is a measure of how badly an atom wants electrons. And if you want to know why one atom wants electrons more than another atom, just ask me and I can find you some stuff on that. Okay?
to try to steal them from other atoms. So in ionic bonding, there are electron givers and there are electron takers. This has to do with whether an atom is a metal or a nonmetal. Okay, so nonmetals like chlorine all have a very high electronegativity. Okay, they are very greedy. They want other electrons very, very badly. On the other hand,
okay, so what you can see is that chlorine has a high electronegativity. And actually, while we're at it, I'm just going to close the door. It's no idea. Come on in. So I'm just going to give you like this little tiny minute lesson on electronegativity, but if you're not interested, you can just ignore me. Okay? So if you're interested, pay attention. If you're not interested, just ignore me. Sodium and chlorine are both in row 3, period 3 of the periodic table, yes? So you'll notice that means they have 1, 2, 3 shells, yes? 1, 2, 3 shells. Now, this electron in the outer shell, it is attracted to the nucleus. How many protons are in that nucleus? 11. So there are 11 things pulling on that electron, yes? However, what is between the nucleus and that electron on the outside? Yes? More electrons. And let's count how many are in between this outer shell and the nucleus. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 11 things pulling that outermost electron in, but there's 10 things pushing that electron out. So in sodium, we have 11 protons, which pull, and we have 10 electrons, which push that outermost electron away. Compare that with chlorine. How many protons are pulling in chlorine? This is sodium here. How many protons are pulling on the electrons in this outer shell? 17. Okay, so we have 17 protons pulling. How many inner electrons do we have pushing away the electrons on the outer ring? Again, we have 8 in shell number 2, and we have 2 on shell number 1. So it's just, again, 10 electrons pushing. So which one, like, and these kind of cancel each other out a little bit, right? The pull and the push cancel. So what is the net pull here? 1. And what's the net pull over here? 7. So it's like there's 1 positive thing pulling there and 7 positive things pulling here. And so chlorine is so much better at pulling electrons towards itself because it has an overall larger positive charge in its core. Okay? If that made no sense to you, just pretend I said nothing. Okay? If it made sense to you, that's great. Like I said, you're not responsible for knowing that, though. Even in the enriched, you're not responsible for knowing the explanation. Okay?
Metals, like sodium, have a low electronegativity. Okay? They're not so greedy for electrons, and they're willing to give them up. So that's why electrons move from sodium to chlorine and not the other way around. They move from the atom with low electronegativity, low greediness, to the atom with high electronegativity. And this is the way it always works in ionic bonding. The metals, like sodium, are the electron givers, and the nonmetals, like chlorine, are the electron takers. Electrons always move from the metal to the nonmetal. And in ionic bonding, because of that, the metals always become positively charged because they lose electrons, and the nonmetals always become negatively charged because they gain electrons.
Okay, so tell your partner, like summarize about metals. Metals are what? They are electron givers. And if metals are electron givers, what charge do they always become? Positive. Chlorine is an example of a nonmetal. Nonmetals are always electron takers. And therefore, if they take electrons, what charge do they become? Negative. Nonmetals always become negative. Metals always become positive.
It's all about electronegativity, the greediness of an atom for electrons. Now I want to talk a little bit about the shape and structure that ionic compounds make. Okay, so we've got sodium here, we got chlorine here, and we've talked about how they get opposite charges and they end up sticking together, forming a shape kind of like this. Okay, but so far we've only talked about 2 atoms, 1 of each. In nature, rarely would we find just 2 atoms. Okay, usually there are going to be a lot more than 2 atoms that want to exchange electrons and combine together. So what happens when we have a bunch of atoms that could all do ionic bonding? Okay, well, what you might want to think of is each pair of these atoms could form a structure kind of like this.
Okay, so this is now on page 26. So you want to flip your page. So every positive ion is going to find itself a negative ion and pair up like that.
Okay, but here's the thing. These guys wouldn't stay separate. Okay, this is super important. They wouldn't stay separate.
Can you think what they would do if they're not staying separate? They're going to connect. And purple is going to connect to green. Absolutely.
Because opposite charges attract, not only in groups of two. Okay, so this positive and this negative, they're attracted to each other, but this positively charged sodium will also be attracted to this negatively charged chloride over here. Okay, so these two things are going to end up connecting to each other because of that attraction, right? And then there's this guy over here, and this positively charged sodium could be attracted to this negatively charged chloride, and this negative charge could be attracted to this positive charge. So this will come together just like here. Okay, and so we start building a much bigger shape. If we get a bunch of these sodium and chlorine atoms getting charges and coming together, we're going to end up with a shape like this. This is called a lattice structure, okay? And you can see how these ions are packed really closely together and how they're making this larger shape, okay? Here we have a negative ion, and it's surrounded by 4 positive ions because they're all attracted together, okay? And over here, we've got a positive ion that's surrounded by a whole bunch of negatively charged ions. And just in general, through the lattice structure, we alternate plus, minus, plus, minus, plus, minus, because all of these opposite charges are attracting together to make this lattice structure.
Okay, so if you didn't catch that, that is at the top of page 27. These positive and negative ions keep packing together in a lattice, Lattice, lattice structure.
So the important thing to keep in mind is that ionic bonding, when you're talking about more than just 2 atoms, it doesn't only make these small groups of 2, but these groups are going to be attracted to each other, and they are going to make much bigger structures that are going to become these lattice structures.
So they're not like molecules, okay? Molecules is when nonmetals bond with nonmetals, and you will end up with little, like in all those pictures you were looking at, you had one atom stuck to another atom, and it was just the 2 of them, and they were just hanging out and being happy together. Okay, so that's one kind of structure, and that's going to take place between a nonmetal and a nonmetal, and we're going to look at that very soon. But when you have a metal and a nonmetal, you're never going to just have a little group of 2 or a group of 4 or a group of 6. You're going to have a whole cubic structure that just goes on and on until you run out of the individual elements. Okay? So this is our lattice structure.
So that's super important when you're thinking about the structure of ionic compounds. Now, as we go forward, we'll probably continue focusing on just 2 atoms at a time. But whenever you see a shape like this, keep in mind that it's just one part of a bigger lattice structure that you get when a whole bunch of these different units come together.
Now, we're just going to walk away from Tyler for half a second and go here, because there's a couple things that I would like to add. So we will often focus on an individual unit, even though they don't really exist like that. There's no way to just grab one sodium atom. Sodium is going to be in a pile of other sodium atoms, like that the metal that we cut over in the fume hood there. Yeah? So you're going to have lots of sodium atoms, you're going to have lots of chlorine atoms, but sometimes we just want to focus on an individual unit. Yes. Yes. Does this really exist in nature like this? No. But chemically it's useful to just say, well, what if we only had one? That's fine. What we call it is a formula unit. A formula unit is kind of like a molecule. Okay, so this thing here is called a formula unit. And because it's grade 9, you can just think of it, it's like a molecule, but for an ionic compound. It's like a molecule, but for an ionic compound. And how do you know that you have an ionic compound? What two things have to come together to give us an ionic compound? Tell your partner. Max? A metal and a non-metal. So honestly, like if you were to call a formula unit a molecule in grade 9, I'm not going to get that wound up about it. But technically it's not a molecule. Okay? But these formula units don't really exist in nature. What we're really dealing with is this thing called a lattice structure, which is also known as a crystal lattice. Okay, so the lattice structure is also known as a crystal lattice. And so we can fill that in here. So we have the lattice structure, also known as a crystal lattice. And if you've ever looked at some salt, it definitely looks like crystals, yeah? Okay, so that's why it's called a crystal lattice. And here is some solid sodium chloride. You can see the alternating positive and negative. Okay, and now we're going to go back to Tyler. Where is Tyler? There we go.
Okay, finally, let's just talk naming really quickly.
Page
okay,
28.
So when this ionic bond forms, we start with sodium, Na, and chlorine, Cl. Okay, sodium loses one of its electrons to chlorine, so that gives us a sodium ion, which we can abbreviate as Na+. And since chlorine gets an extra electron, it becomes a chloride ion, Cl-. Okay, now we call it chloride because...
You're ready? Yeah. Yeah, that's okay. Let's see where we are. There it is. And let's get your periodic table. There you are. Thank you. All right, what do you notice happened to the name of the metal? When it became an ion, it went from being an atom to an ion. What happened to the metal name? Nothing. Nothing happens to the metal name. The metal name just stays the same. The metal name just stays the same. What about the non-metal? It changes to "ide." Okay, so always just the non-metal changes its ending when it becomes an ion.
Chloride is the negative version of chlorine. It becomes a negative ion and it becomes chloride. Sodium, on the other hand, we call it sodium whether it's neutral or whether it's positively charged. So we have a positively charged sodium, negatively charged chloride, and they stick together. So now they make a compound because these two things have connected, okay? And the compound, we call that sodium chloride, and we write its chemical formula as NaCl. Now, here's one common mistake that people make that I don't want you to make.
Okay, so we're just going to pause so you can fill in any blanks that you need to. That one box up at the top left, I don't know what it's doing there. There's nothing that goes in there. I think it's a mistake, so don't worry about that box at the top left. Okay? Yeah.
Okay? They're writing the formula for sodium chloride, and they see that this has a positive charge and this has a negative charge. So often, they'll write it as Na plus Cl minus. Now, that's not right. Don't do it. Okay, it's true that sodium does have a positive charge and chlorine has a negative charge here. But when...
What is the overall net charge when you put an Na plus and a Cl minus together? 0. So that's what we actually write for the whole thing. We don't write in those individual plus and minus charges. We just leave them alone, okay? And we just write the overall charge of the compound, which is 0.
When the two of them come together, the positive and the negative charge, they cancel out. So it's like the whole thing combined doesn't really have any charge anymore. So that's why we don't put the plus and the minus when we're writing the chemical formula. It's just NaCl. We leave out the plus and we leave out the minus. Okay? One other thing that sometimes happens is when people are asked to name this compound, okay, so like the name sodium chloride, they try to keep these charges in. So they call it sodium plus chloride minus. And again, you don't want to do that because we don't keep the charges. So don't call it sodium plus chloride minus. It's just sodium chloride, NaCl, even though these atoms still have a charge. Because they're like balancing each other out in this compound, we don't worry about the charge when we're naming it.
Okay, the other thing I want you to notice is even when we write sodium ion on its own, do we write the plus sign beside the name? No. Okay, and the minus sign doesn't go by the name. It only goes by the symbol. Okay? All right, very good. And we're now going to go to page 30. Okay. Let's take a look at page 30 together. Names and formulas of simple ionic compounds. So when we name things, actually, let's just take a quick look at the periodic table. On our periodic table, where are the metals? Where are the metals on the periodic table? They're on the left. Okay, so all of this over here, blah, 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 blah. I'm not quite sure I got that border right, but it's close. Okay, and over here, these are all our metals, yes? All our non-metals are over here. Okay. When we write the formula for an ionic compound, can you guess which one goes on the left and which one goes on the right? Does the metal go on the left or does the metal go on the right? The metal goes on the left, just like on the periodic table. The metals are on the left on the periodic table. The metals come first on the periodic table. When you're writing the name of a compound, the metal always comes first. So the metal comes first and the non-metal always comes second. And I think you guys are you've already done this a couple of times. Basically, you take your two elements and you say, I have a compound between magnesium and oxygen. Magnesium is the metal, and oxygen is the non-metal. So which one do we write first? Magnesium. So magnesium comes first. And then oxygen changes its last name to oxide. Yeah. Okay. Now, what if we have a compound between aluminum and nitrogen? Nitrogen, is nitrogen a metal or a non-metal? Non-metal. And aluminum is a metal. So, which goes first in the name? Aluminum. And nitrogen, its ending changes to ide. Okay? So that's how you do the name. Formulas, you've already seen some formulas. You saw some in the POGL activity. Do you remember seeing things that was like SQ, it was like R, SQ2R? You remember those? Those are sort of like the formulas we're going to do, except for we're not going to use SQ and we're not going to use R. We're going to use the symbols from the elements on the periodic table. These little numbers down at the bottom, say we have our SQ2R, that little number down at the bottom is called a subscript. If you have a submarine, where does a submarine go? It goes under the water, under the sea. And if you speak any Latin-based languages like French or Italian or Spanish or any of those, in French, the sea is mer. In Spanish, it's mar. So submarine means under the sea. Okay? So sub means below or under. Script, if you think about script, maybe if you're, going into a play, you get the script, yes? So the script is the writing of the play. It's not the acting of the play, it's the written down version of the play. So script means writing. Okay, script is writing. So if we have a subscript, where does it go? It goes below the writing. Do you see how this little 2 here is below the writing? Because it's below the writing, we call it a subscript. Yes. Yeah. So the subscripts are usually little tiny numbers, and they tell you how many of an atom or an ion are present. So let's say that we have a compound between sodium and phosphorus. And I'm just telling you, at this point you don't know how to figure this out, or maybe you do, maybe you're really clever. A compound between sodium and phosphorus contains 3 sodium ions and 1 phosphide ion. So let's name that compound. The metal goes first, sodium. The phosphide goes second, the nonmetal. Right? So we have our metal first, and then we have our non-metal second. Also take care, it's phosphide, not phosphoride. Okay, phosphide. Now, if we want to write the formula for the compound, there are 3 sodiums, so we put a little 3 down beside the sodium, Na3. That means there's 3 sodium atoms or ions. And there's only 1 phosphide, and if there's 1 of something, we don't write a subscript if there's only 1. Now, sodium is in what group? Sodium is in group. Oh, people are still writing. I'll wait until you're done writing. Then I'll ask. What group is sodium in? Group 1. Therefore, it has how many valence electrons? Tell your partner what a valence electron is. What is a valence electron? What's a valence electron? Yes, Anne.
Electrons on the valence shell, aka the outer shell.
Yeah, so it's an electron on the outer shell. How many electrons are on the outer shell of group 1 elements? Guess what? It's really easy. Group 1 has 1 valence electron. And if it has 1 electron in its outer shell, what does it want to do to become stable? It wants to give this one away, yes? What happens if something loses 1 electron? What charge does it become? Becomes positive. And that's why our sodium just says plus. If it just says plus, how many pluses is that? Just plus 1. Okay? So we have sodium plus, sodium plus, sodium plus. Yes, Aaron? It's just H plus, and its nucleus, honestly, just most of the time contains just 1 proton. And in fact, when we're in grade 12 chemistry, we actually refer to the hydrogen ion, the H plus ion, as a proton. And so we have acids, which are proton donors. They'll give a hydrogen ion away, and bases are proton acceptors. They'll accept a hydrogen ion. So yeah, you're absolutely right. It's kind of a funny little thing. And hydrogen can actually do both. It can either fill up its shell and become H minus and become hydride, or it can lose an electron and be a hydrogen ion. So it's a weird little one, that hydrogen. What is our total positive charge if we have 3 sodium ions? Each sodium is plus 1, and we have 3 of them. So our total charge is 3 plus. Now, phosphorus. What group is phosphorus in? You should have your periodic table kicking about. It's in group 15. So phosphorus is group 15. So how many valence electrons does phosphorus have? Phosphorus has 5. Okay, it doesn't have 15. We always just get rid of that one at the beginning. And we say phosphorus has 5 valence electrons. Now, if an atom has 5 electrons in its outer shell, does it want to lose electrons or gain electrons? It wants to gain. How many? 3. If it gains 3 electrons, what does its charge become? -3. And that's why phosphide ion is P3 minus. So we have a P3 minus. So that means our total positive charge is 3 plus. Our total negative charge is 3 minus. And the entire thing, the net charge is how much? 3 positive, 3 negative, the net charge is 0. Sometimes my pen does crazy things. That was supposed to be a single line. Net charge is 0. All compounds, the net charge should be 0. Yeah. Aaron. Where the Bohr model doesn't work? This is kind of weird, but to be honest with you, we can use the Bohr model for, well, we can't use the Bohr model, but we can use the number of valence electrons. We can predict it for all of group, well, obviously group 1 and 2 are okay, right? Okay, so group 1's okay, group 2's okay. We can use it to say everybody down to about here has 3 valence electrons. Actually, quite frankly, everyone in this group has 3 valence electrons. The electrons that fill in here, these 10 electrons, they just don't count towards the valence electrons. They're actually on a shell that's closer to the nucleus, which is why it's kind of bizarre and why the Bohr model stops working super nicely. But you can pretend that those 10 electrons don't exist, and you can just be like, okay, my outer shell will have 3 electrons, 4 electrons, 5 electrons, 6 electrons, 7 electrons, and then either full for helium is 2 or the other ones are 8. Okay, so when we say valence electrons, it actually does apply to everybody all the way down the column. What? What groups are? Sorry, I'm just not hearing you. Oh, the lambda, they don't actually have group numbers. Or sometimes they're called like 3A, 3B, I don't know. They will, yeah. Yes. They're technically in between groups 2 and 3, but we don't call them group anything, really. Okay, so the lambda-9s and actinides, we don't give them group numbers. Okie dokie, back here we go. So now I want you to remember always that in an element symbol, the first letter is always a capital. The second letter is always lowercase. So KF, how many elements? 2, one capital, 2 capitals. It's made of potassium and fluorine. What would we name it? Potassium fluoride. Okay, so potassium and fluorine, its name would be potassium fluoride. MgBr2. How many elements are in MgBr2? 2, because we have 2 capital letters. So it's 2 elements. The elements are magnesium and bromine. What would we name that compound? MgBr2 is named magnesium and bromide. Did I worry about the little number down here? Nope. In the name, you don't put any of those little numbers. No numbers in the name. How many elements are in NH4Cl? 3. I've got an N, I got an H, and then I got C with L for chlorine. So it's made of 3 elements, nitrogen, hydrogen, and chlorine. And you don't know how to name that yet, and you won't know how to name it until Unit 4. Yes?
So I was wondering, how can you tell the difference if it was, for example, that? How can you tell the difference between a capital I and a L?
Every font I give you, capital I will have crossbars on the top and on the bottom. I've actually gone really out of my way to find one. It's hard to find one that does both that and looks nice. So that's why this font is the one that I use for everything, because it actually does a crossbar on the top and bottom of the I. So I will always look like this. L looks like this, and 1 looks like that. So they all look different, which is really important for chemistry. Okay? Now, sometimes if you see Times New Roman font, are you guys familiar with Times New Roman? The L looks a little bit like a 1. It's never going to be a 1. It's always going to be an L. Okay? Because why would you have a 1 beside a C? Okay? Eventually along the way, you'll just get used to everything kind of looking like it looks, and you'll be like, C1, that doesn't make any sense. It must be Cl. Okay? If you're interested, this compound, the nitrogen and the hydrogen together make ammonium chloride, but you wouldn't be expected to know that yet. So don't write it down unless you like that kind of thing. Okay, because you're not expected to know that. How many elements in NaNO3? 1, 2, 3. And this one is actually called sodium nitrate. The N and the O together are making the nitrate. But again, should you write that down? Probably not. Okay. In this unit, Unit 3, we're only going to consider compounds made of 2 elements. Oh, and look at this. I will always use a font where the letter L and the capital I are significantly different. So when you see this, Is this Ci2 or is it Cl2? Cl2, okay? And that's a chlorine molecule, so what you've got is you've got one chlorine bonded to another chlorine. And when I actually write it, I usually write my L's like this so that they look really different, but you feel free to just write your L's as lines. That's totally fine, okay? So there is our Cl2. This is a Cl2. What do we call it when we have two atoms stuck together? That is a molecule. Whoops. And it's a molecule made of two chlorine atoms. Is this a compound? Tell your partner, how do you know if something is a compound? Max. It is not. You're absolutely right. It is not a compound. What does something need in order to be a compound? Yes.
One or more elements. I mean, two or more elements.
Yeah, I thought that's what you meant. Yeah, two or more elements. And here we only have one element. So this is a molecule of an element. Ki, give you a minute to write there. How do I know that Ki is an ionic compound? K is potassium, which is a metal, and I is a non-metal. K is in group 1. How many electrons in the valence shell of group 1? 1. So what does K do when it forms an ion with its 1 electron? K has 1 electron in its outer shell. What does it do to become an ion with that 1 electron? It loses that 1 electron. If you lose a negative, if 1 negative goes away, what charge do you have left? 1 negative is gone, so you have 1 positive. So that's why K is positive. Yes? Yeah. Iodine is group 17. How many valence electrons? 7. If you're in group 17, you have 7 valence electrons. Does it want to fill up its shell or empty its shell? 7 valence electrons. Does it want to get rid of 7 or gain 1? Gain 1. If you gain 1 electron, what is your charge? Negative. Negative what? Negative how much? Negative 1. And that's why iodine is negative 1. Okay, so we've got a K and an I. Could you write the name for this compound? Feel free to use your periodic table. If you have lost your periodic table, I will have some more available for you tomorrow. I will make them yellow and lovely for you. Yes. That is potassium iodide. Yes. Look what we've got here. Is that a Cl or a Ci? That is Ci. So I have C, which is carbon. I have I, which is iodine. Is carbon a metal or a non-metal? Carbon is a non-metal. Iodine is a non-metal. Is this an ionic compound? Non-metal plus non-metal, is that ionic? No. So it's a different type of compound that we'll be focusing on a little bit later, but just to get you familiar with the word, it's called a covalent compound. And it has a different naming system. So I'm not going to confuse you with the name right now. Okay, if you're interested, you can come ask me about it later. And what type of particle is this? This particle here. What type of particle is that? That is a compound isn't a type of particle. A compound is a type of substance that contains two or more elements. You're absolutely right, it is a compound. But the type of particle is what? We have 5 atoms stuck together. That is a molecule. Does anyone remember what we called this thing that's made of a single positive ion and a single negative ion? Sadly, the initials are FU, which is rather unfortunate. I'm sorry. Yes, it is a formula unit. There's a few things in chemistry where you're like, I'm just sorry, that's just the name. We used to have follow-up questions and I tried to abbreviate it. And I'm like, no, we cannot call them FU questions. That's just a bad thing to call them. And then I was like, FUQ, and I'm like, oh, that's bad too. I'm like, no, there's just, you have to write out the whole thing, follow-up questions. Just not good. And then back when we taught astronomy and we had to name the planets, oh good Lord, when we got to like is it the 7th planet? Oh my gracious. Like, could not get past that one. Oy, oy, oy. So many things. And if you take Chemistry 11 enriched with me, you'll get the worst one ever, but you have to take Chem 11 enriched. I'm not saying it till you're older. Okay. So if you guys, for homework, wouldn't mind doing number 1 here. Okay. Number 1, because you've been so patient, we've sat here all class and I've gone yappity, yappity, yap, and you've been like learnity, learnity, learn. And so all I'm giving you for homework is number 1 on page 32. Page 32, number 1, that's it. Okay? Enjoy it. You could even maybe finish that before the bell rings. You've got like, yeah, you got 3 minutes. You might even be able to finish it before the bell goes. The name. Folks, you're putting the name, not the formula. The name, not the formula.
That's like, so it's like calcium and then fluoride and then sodium.
Yeah. Yeah. We always change that because when pieces of metal in on it, so this one's going to be giving electrons to that one. So this one becomes positive, that one becomes negative. And positive ion always keeps its name, the metal always keeps its name. The non-metal, when it becomes negative, it becomes anti. Yeah.
That was just for fun. It wasn't even. But we need that for something interacts.